And where is our earphone? It's not needed, right? This one?
Yeah, take it off. Because
Okay.
it's not going to hear you if you don't have a microphone.
Ah, okay.
That's why.
So I just put it here?
Yeah. This one in your pocket.
Yeah.
That's it.
Is it on?
Yeah.
Good. Okay. Should we start? Oh, people are coming. Maybe we can wait one more minute. Sorry. Okay. Should we? Oh. 5 more minutes? Okay. Okay. Yeah. Exactly. So that's why I have so many things to cover. So welcome to the lecture 4 of this series. So today we're going to cover 3 important topics. One is the theory of correlation, data normalization, and the chi-square test. Okay. So last time, many of you asked this question, right? How to check if the data is normal or not. So to be normal, not to be, that's the main question, right? So I think I should discuss this before I start my real topic. In statistics, there are many tests by which you can actually test if your data is normal or not. Okay? So maybe we should wait for them to settle down. Yeah. Yes. So in statistics, as I said, that there are so many tests by which you can see if the samples has a normal distribution or not, or has been extracted or derived from the normal distribution. Yeah. So first choice would be the Shapiro-Wilk in the statistician. That's the first choice. Second choice is the Anderson-Darling test. Third one, Post test, and the fourth one is the Kolmogorov-Smirnov test. So if you see in 1980s, 90 people have been using this test, Kolmogorov-Smirnov. But there are so many advancements in this test, like making it more robust and non-parametric. So my favorite one is the Anderson-Darling test, right? Because this Shapiro-Wilk is a bit, well, it's not straightforward to calculate, right? In MATLAB, it's very easy to calculate. So let's see how this Anderson-Darling test look like. So the null hypothesis of the Darling test is that the random sample or your experiment sample could have come from the normal distribution, yeah? And this is a very simple command. It's like AD test, and this X would be your samples, and H would have value 0 or 1. So if it is 0, means do not reject the null hypothesis at significance level, right? And H equal to means that you reject the null hypothesis, and your null hypothesis that the sample is derived from normal distribution, yeah? So let's see actually an example, really. So I just took this 30 samples, okay? These are the 30 numbers. And I have calculated this 30 numbers from the normal distribution. So there is in MATLAB, you can actually extract it. So because I wanted to show you how this test works, right? Because then we can go back and check the validation. Because we know a priori that this sample is a normal distribution, right? So if you apply, and if you first plot this histogram, then one can say, okay, yeah, it looked like Gaussian, right? It looked like Gaussian. So if you apply this test, the test would say H is equal to 0, yeah? Meaning that you accept the null hypothesis, that yes, it has been derived from the Gaussian distribution or normal distribution. But this is not that impressive because we know a priori that we have. So what I do, I randomly sample 7 samples from this population, because for us this is now our population and this is our sample. So I randomly sample 7 points from this 30 samples or populations. And when I apply this, first I see the histogram, right? And just by looking at the histogram, one would say, okay, this cannot be a distribution, right? It cannot be Gaussian distribution. And this is what you exactly encounter during your experiment. Because in experiment, you have a fewer sample size, right? Like 7 samples. And when you plot, you see the histogram like this. And then you say, okay, now I cannot use any parametric test. That's not the case. Here is the. You accept null hypothesis, yeah? Meaning that this sample has been derived from a population which has a Gaussian distribution. Basically, you can apply all parametric tests on this one. This is very important. This is how you can, calculate if your distribution is normally distributed or not. You can also see the Lilly-Force test. So H is equal to 0, meaning also according to this test that these samples are normally distributed. But if you apply the Kolmogorov-Smirnov, it says it rejects this null hypothesis, meaning that according to KS test, this is not normal distribution. So you see the power of, and you can see it here. So AD has more power than the KS, followed by use Anderson-Darling test, yeah, to check the normality. Okay, let's see and look at the correlation. So correlation can be also called as a dependence or association, right? Correlation is a statistical relationship, which is also called as a covariation between the 2 random variables. So if you have an experiment where you have more than 2 variables, so you can one by one and see how they are correlated, right? Each and every variables. And how to quantify this correlation? By the correlation coefficient. Example, correlation between 2 different gene reporters. One is labeled with a GFP, is labeled with M cherry. Yeah, just imagine this 2 gene protein, right? Gene reporters, which is labeled with the GFP and M cherry. And then you're interested in finding the relationship between the GFP and M cherry. Yeah? And if you plot this is a scatter plot. You just plot X versus Y, and you see this plot here. So one can say that as GFP increases, M cherry increases. Well, another case would be that if the GFP decreases, M cherry increases, or the vice versa. The M cherry increases, right? And there can be some other fuzzy state in between these 3. But one can just say that, okay, it is increasing or decreasing or remains same, but one cannot say quantitatively how much, right? And also the correlation does not imply the causation. So in the correlation, you can only correlate, like I can say that GFP is dependent or associated with M cherry, or whatever the gene related to GFP is associated to M cherry gene, right? But one cannot say that the GFP is expressing because of M cherry. No, it is not possible. I mean, through correlation, it is not possible. But how to check the causality then? Any of this? How to check the causality? We have seen in lecture number 1, right? So because the causality it's a real evidence, right? So if you need more evidence, meaning that you have to go for a randomized control trial or systematic review, right? You have to do the systematic experiment to see the GFP and M cherry. Then you can conclude that they are causal, basically, right? So the types of correlation coefficients. So there are 2 categories of types of correlation coefficients. One is moment correlation coefficients, called also PCC, right? It's a measure of the strength and the direction of a linear relationship. So if you are interested in finding the linear relationship between the variable A and B, then you have to use Pearson's correlation coefficient. This is a parametric correlation coefficients, okay? Also, category of correlation coefficients. So if you're not sure about the distribution of your data, see what is monotonic between two variables. Kendalls tau, it look for the proportion or the portions of the ranks between the two variables. And there is this Godman and the Kruskal gamma. It is normally in biology. I have never seen people using this, so we're not going to discuss this. Okay, so we're going to only discuss these three correlation coefficients. So let's see this Pearson's correlation. So it was used or discovered by the Carl Pearson. He was a statistician and a mathematician. So what he says that he came up with a formula, which you can see it here, right? And according to this formula, this x and y basically are the two variables on which you want to quantify the correlation. And the value goes from +1 to -1. So how to interpret? So 1 is the total positive correlation, 0 is no correlation, while the -1 is the total negative correlation, right? And one can have the values in between these two, but it can never go from -1 to +1 beyond that. So we are not interested in this formula, right? Because these days we have a sophisticated and the commands. For example, in MATLAB, you just type the core coef, x and y, and then you get this R and P. Similarly with SPSS and SAS, whatever the statistical software you use. So let's see the geometric interpretation of PCC. Yeah. So we have seen this example of GFP and M-Cherry, which is a kind of positive correlation. So how do you interpret this? So first, I would say that okay, I will try to draw a line, which would be so I will try to fit a line which would be best representation of this data. Yeah. So I can have a multiple choice. I can have this line, I can have this line, this, 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 and this, and this. There are many options, right? But how to choose a particular line? So of course I had to select a line which would minimizes the mean square difference between that line with respect to all the data points, right? This is the whole algorithm of PCC inside. So, and this is how, once you get the line, you get basically the intercept and the slope. Intercept and slope is called as a regression coefficient. So you can say that GFP is dependent on A plus B times M-Cherry. Yeah? And if B is positive, it's a positive correlation. B is negative, negative correlation. But again, we haven't reached to the level of quantifying the numbers, right? This is just a geometrical interpretation. And this is where the PCC is useful. So using PCC pull all this data into that formula, and that with that R value, right? And that R value, the geometric interpretation, you can see that if the line, if this is 3 points, and if they are collinear, meaning that they place on the same line, then it is a perfect negative correlation. Yeah. If they are dispersed around this line, then it is a negative correlation, but it is less than, I mean, it is close to the 0, right? It cannot be -1, which is exact negative correlation, right? It will be a bit less negative. Similarly with the positive correlation, this is a perfect positive correlation, and this is completely random, right? Because you can have multiple lines which would have a different slope, which has no meaning, right? So it's completely random, so there is no correlation in this case. But again, let's interpret again the Pearson, because it's very important, right? Most of the time we report this in literatures. So once you have this, what you get out of this correlation coefficient is this two values, correlation coefficient and the p value, right? So for this particular example, if I got this r equal to 0.8 and p is equal to 0.002, what does it mean? So let's interpret. It has three meanings. First meaning is that the GFP and M-Cherry are positively correlated with. Second interpretation is a level of significance all the time, right? Most of the time. Meaning that we reject the null hypothesis that there is no correlation. Meaning that this value is statistically significant, meaning that there is a statistical significance or statistical positive correlation between G. Yeah? Because it doesn't matter what number you have, if the p-value is not significant, it has no meaning. Yeah? And the third one is very important, and I think most of the time people just report these two numbers. But third one is also important. That is called the R-square value. It's called as a coefficient of determination. So whatever is your R value, you square it, that's a 0.64. What does it mean? It means actually real value, that the 64% of variation in GFP can be explained by the variation in MJ. This is very important. If this had been 1, meaning that there is a 100% variation, can be explained by GFP and MJ. So having only 0.8 is not a good idea, because if you square all the 0.8, it will reduce the number. That is basically real meaning of correlation. So I have seen people report at 0.9, but actually it's not 0.9. You have to square it, right? That is a variation variable. And p-value is very important. Seen that the p-value, the Pearson's correlation can give you the strength, meaning that it can have a value from -1 to +1. And it can give you direction. So it has a strength and direction. And it can be depicted from this picture, right? What is the limitation? Limitation is that it is not sensitive to the slope, meaning that if you have the correlation, positive correlation, like this, like that, it will still have the 1 value. So it is independent of the slope, okay? Similarly with the negative correlation. Another limitation or the shortcoming is that it is not sensitive for the nonlinear relationship, meaning that if you have a data like this, okay, x-axis and y-axis, do you think that there is no correlation here? I don't think so, because I can see that there is a correlation, meaning that there is an association, right? It's just for some time point or for some x domain, it decreases, then increases, decreases, and increases, right? So there is an association. We cannot say it's a zero association. In this case, the Pearson's correlation fails, right? It gives you 0 value for all of them. And also it is affected by the outliers, you see, because if there had been no outlier here, the line would have been here, right? But because of this outlier, the line would be here in order to minimize the error, right? And this is not true, because this would reduce our correlation coefficient. Yeah? So if you remove this outlier, the line would be here. So it is affected by the outliers, right? So in such cases, if you have outliers and all this issue, then one can use this Spearman's correlation coefficient. But there is also one condition here. It can be only applicable for the monotonic function, meaning that this is a non-monotonic function, meaning that it decreases, increases, decreases, and increases. It is no one monotonous relationship, right? It should either increase or decrease all the time. So you can see here in this sigma plot, right, the Pearson's correlation was 0.8, but the Spearman is perfectly 1. And this is the beauty of Spearman correlation. So even if it is non-linear, as long as it is monotonous, increasing, it will give you a positive relationship. And it is also as good as the Pearson's when there is a randomness available. So it's nearly the same, almost same value. And this is a significance of having using the Spearmans in case of outliers. So because of the outliers, the Pearson's was 0.67, but the Spearman came out to be 0.84. So it is not affected by outlier that much. So, and this is how you write in MATLAB. You just a core command and then say type Spearman, similarly with the Kendall, right? We're not going to see the Kendall. Kendall is a bit complicated. I think it's going to take another 20 minutes to explain you. But it's based on the concordant pairs and discordant pairs, okay? But always the Kendall would be less than the Spearman. But this is how one should do, yeah? Whenever you want to quantify the correlation in your experiment, step 1 is the plot scatter plot. Always plot first before doing and quantifying the Pearson's value or value. Check if there are outliers. Step 2, check if the plot is linear. If it is linear, then apply Pearson's correlation coefficient. Yeah? If no, then check if the plot is monotonic or monotonic relationship. If it is, then apply the Spearman's rho. Yeah, you can quantify the Spearman's rho. The Spearman's will also give you the p-value and the rho, right? And if none of these satisfies, then apply the Kendall. That's always a last resort, okay? Because of course it's a non-parametric, so the power will reduce, right? Let's look at the data normalization now. So, so first, in order to understand data normalization, let's understand why data normalization is important, especially in the biological experiment, right? So, typically this would be a protocol of any experiment, right? So one can have some samples from human or animal or whatever, the plant and all. One can extract tissue, cells, or one can different entities of that living organism. One can prepare the samples, then acquire images, do image analysis, do data processing, and then you do data visualization. And then you get an observation, and then you apply statistical method on that. But there are variations in every stages of this block set. The variation in biology would be here. Variation in chemistry would be here. I think this is the easiest way of understanding. That's why I thought it's a good idea to put it that way. Variation in physics would be from microscope or whatever, the systematic instrument and all these things, like if you work on proteomics, for example. And the variation in algorithms, like these days, we use Imaris or whatever, all the softwares, scan. So there will be a variation in algorithms and programming. So we know that how to get rid of these variations. We have seen in lecture number 1 with like reducing biases. That's why we have a technical replicates and biological replicates, right? We didn't have time to see the biological replicate. We're going to see it in lecture 6. Yeah? But the point here is that in spite of screener's ability to reduce the bias, there will be a variation from one plate to another plate, or one sample, or one experiment to another experiment, right? So in order to compare the experiment to experiment, it is important to have the range, the common range of the data. And that's why we need normalization. So one basic, the first basic way of, straightforward way of computing normalization or having normalization in your data is normalization. So what you do here is that you choose x mean and x max, and for every data sample, you subtract basically the minimum value and divide by the range maximum. Let's see the example. So we have an example here. So let's say I have 6 numbers here. The minimum value is 3, maximum value is 66, right? So when I plug this information to this formula, every value is affected, right? And this is the beauty of this one. So the 3 value, which is the lowest, has got 0 value. The highest has got 1 value, and every others has got in between. You map your data into 0 and 1, right? But then one can argue that, okay, I'm not interested in 0 and 1, but I'm interested in specific range, right? One can also use this formula for that. So you just choose A and B, meaning that if you want to map the same data into 100 and 200 range, one can apply this formula, and then one can have this. So you can see that the lowest value has got 100 value, 100 number, highest has got 200, and everything else has got in between value. Yeah? Z-score normalization. This is very important and mostly useful. I mean, most of the time people use this data normalization technique. So what you do is for every data point, so you subtract basically the average of the entire population from each and every samples and divide it with respect to the standard deviation. Yeah? So let's say an example. So you have this example of the 6 values here. Well, 7 values here. You compute mean, you compute standard deviation, and you just plug these values into this formula. So every value minus the average value divided by standard deviation. And this is how you get the value here. But how to interpret this? I mean, why would somebody wants to do this? And what is the significance of doing this? The significance of doing this is this one. We have seen in lecture number 1 the standard deviation, right? What it does is that no matter what kind of data you have, it always map your data into a standard normal distribution whose mean is 0 and it has a unit variance. Okay? So what does it mean is, let's see, what was the average? Average value was 9.97, right? And this 11.7 is more than the average, right? So it would come into the right-hand side of the mean value. And this is what it got. It's a positive value, right? Those which are less than the mean value, let's say this 8.54 has got a negative value. So it has a very, it introduced the information that how symmetric your data is across the average value. And also you can say that how much standard deviation, how much the standard deviation is there for that particular data. For example, 1.15 meaning that it is 1.15 standard deviation away from the average value. This is what it means actually. Yeah, because it's a unit standard deviation. And then if you map all your experiment to this Z-score normalization, you can compare the data. Yes?
I didn't understand why on that side and plus again on the left side.
So this 12.07 has got a positive value, right? Yes?
Because it's above the average.
Yes, exactly.
And why is right next to it the minus?
This is because 8.30, which is less than average value of 9.97.
It's not related to the curve, so it's just the same numbers in order.
Yeah, exactly. Yeah, it's the same numbers in order. I think I should have given an arrow in order to mention, right?
Yeah,
So that's just, so we have the 7 numbers, and 7 numbers has got a different value now, the 7 different values via this Z-score normalization. So it's basically a difference of the mean per standard deviation. So now we have a one standard deviation scale. You can see here the Z-score. You see here Z-score, this thing? That's why I also put the Z-test actually. We use the Z-test. Z-score, it has a 0 value, +1, +2, +3. So we can say that this number, which is the 11.7, it is one standard deviation above the average value, meaning that it may not come into this 68% of the population, which we have seen in lecture number 1, right? Okay, but just to give you an example of how this can be useful in the image normalization, yeah? Because I haven't got this example, so I got this example from my PhD work, right? So let's say, because in our time, we have collected the cancer woman mammograms from different scanners, and the controls are from different scanners. So in your case, you can imagine that you are doing some experiment using Leica microscope or Zeiss microscope, and then you difference in the intensity range, even if it's the same biological sample or a different or the same protocol, for example. So there will be a difference. For example, in this case, there was a difference between the control and cancer cases, and that was difference is because of the scanner. It wasn't because of the biology. Okay, it was a scanner. So it is very important to correct that difference, and that is done by the Z-score normalization. So this is a cumulative distribution function of the intensity of all the mammograms of cancer, and then we have to do feature extraction and classification. Okay, yes.
Case, for example, you would have to match.
Right, between or distinguish between cancer cases and versus intensity curve like that, exactly overlapping with each other. For example, in your case, if you want to compare wild type versus knockout, you try to collect all these images from the knockout and the wild type and plot the histogram or the CDF function and see if they are exactly similar. Then you extract your extraction, feature extraction on that. If you do not do this, this is the point, this is what I was supposed to say. So let's say if I do not do this, and if my aim is to discriminate between cancer and control, I would get discrimination very positive, significant discrimination, but that discrimination is not because of the biology, it is because of the scanner effect. So that's why it is very important when you plot wild type versus knockout, make sure that there is a homogeneity, right? And they are in the same, it is not because that it's because they are different in the intensity range, yeah? No, so think about this one. So if you go back here, in this case, imagine that you have this, let's say this is a very this has been derived from a very systematic experiment, right? And the other one has been derived from a very rough experiment, right? It doesn't matter. What matters is that you project all your data into the average of this population and divide by the standard deviation. So you are mapping basically, you are just mapping, but not, you are mapping what is the homogeneity, what is the overall distribution of this group. I'm not talking. Yeah, intermixed with that, rough and the systematic. I understand your point. So you just have to do it independently, this one. Z-score normalization in systematic, different, and then rough, and then compare. Yeah? So, yeah, so one should do that only after doing this. Yeah? And one should always check if there is a difference in the. This is very important for the equalization experiment, right? Because that's our main intensity. Normalization of high content screening data. So these are the sources of systematic error and random error in high content screening, right? So errors caused by reagent, anomalies in liquid handling, variation in incubation time. I think Yuta and Claudia would know more than me here. I just collected it from this reference. But there are some variations, right? And what we want ideally we want that the feature range observed across the different wells with the same treatment should be the same. Yeah, they should look similar. And also the feature distribution of the controls in the different plates should look same. So we have to do interplate normalization. And in interplate normalization, let's say we have the different plates. This is a typical layout of the plate. The red one is this negative control, right? And how to do this interplate normalization? The first and very basic way of doing this is the percent of control, meaning that you divide each and every sample by the mean value of the control. It can be negative or positive control, depending on what is your experiment is, right? Second method is that the normalized percent inhibition. Let's say if you have a different variety of the control, let's say high control and low control, then you can also use this formula. So for every samples or every well value will be subtracted from this high and low value. And this is how you get. Third one is the percent of samples, because it may not be always the case that you have a control. What if you do not have a control at all? You just have a different experiment, I think, in the dance stem perspective, right? You have a different conditions. So in that case, one should just divide everything with respect to the mean of the samples. That's also one way, right? It may not be the exact and right way, but that can also be a way to normalize the data. Yeah. And then one can always use Z-score normalization. We have seen that. But there is one more, it's called as a robust Z-score normalization. So we have seen this, right? And this one is that, let's say, if your data distribution of the wells, different wells, are not normal using this Anderson Darling test, then one can use this robust Z-score method, where you subtract the median value of all the wells, divide by the median absolute deviation. Okay? Well, the median absolute deviation is similar to standard deviation, and this one is similar to mean, right? And this, what you do is you subtract every value from this median value, or you subtract median from every value, and then the median of that difference. That's a median absolute deviation. Intraplate normalization, yes, mostly if it is you have a special effect, or the one called as a age effect, right? If you have an age effect, then one can think of the intraplate normalization. But this occurs only if you have so many plates, and when you have I don't know, maybe Yuta would tell you some evaporation artifact, right? Because you can see here, this is an example from this particular source, that you can see that this is the heat map of the wells. And they are the same examples. I mean, they are the same treatment, they are the same samples, but just because they are on the edge, the evaporation rate was more, so when you quantify this plate, it is affected. Your measure is affected, right? So you have to counterbalance for this edge effect. The solution is that you avoid age effect by leaving the age wells, just not putting any samples over there. Or if you cannot avoid it, because if you are going for the big screening, then one cannot afford to lose these positions, then one can use a B-score. It's called as a Tukey median Polish algorithm. Right? It's a bit complicated, right? So rows and columns and things, we're not going to see that. So we finished the data, and now we're going to see the chi-square test. Yeah. So last time we have seen which test statistics to be used, right? So we have to ask these two questions, and we have seen this example where we have seen the difference of means. If this is your question, then you can have a different option: Z test, T test, ANOVA. Last time we have seen this. Then we have seen, but we haven't seen the F test. This is not important, right? And then we have seen last time the difference of medians. That's a non-parametric test. And today we will see this one, the association between the categorical data. And then we will see the chi-square test and Fisher's exact test. You have to apply Fisher exact test when your sample size is low. And when you have enough sample size, then you can apply chi-square test. So first look at the chi-square test. So the chi-square was introduced by Carl. He was also a British biostatistician, University College London, and he was a senior colleague of William Gosset. The last time we have seen the student T distribution, so they were actually working together. So according to with the chi-square test, you can actually answer 3 questions. Test for the comparing variance, meaning that to test if the given sample has been drawn from a normal population with a specified variance. So if you want to test, you have collected your samples, you have quantified your standard deviation, and now you want to check if that deviation is to the other standard deviation of population standard deviation. It's the same like mean, like last time we have seen mean with a T test and the Z test with the one sample. Similarly, you can check that. And what it goes is like you compute the standard deviation. Right? This is a variance basically, the variance of samples divided by variance of population. And this is, last time we have seen, this is called as a degree of freedom, right? N-1 degree of freedom. And it turns out that this ratio has atypical curves depending on the different degree of freedom. That's called as a chi-square distribution. We're not going to go into detail with that, right? What we are interested, and also there is another one, is to test the goodness of fit, meaning that last time somebody asked about Poisson distribution, right? Poisson distributions. So using chi-square test, one can also check if the that you collected has a Poisson distribution or any. It is called as a goodness of fit. I think this is not also important as far as biology is concerned, right? We are maybe interested in this one, comparing the 2 groups with a dichotomous outcome. Dichotomous meaning that when only 2 output, yes or no, positive or negative, or it can be categorical data, meaning that high, low, and medium, like that, right? In such cases, how to compare the two proportions. So the chi-square will give you this help. So it is very important to understand the observed and the expected. So what you see is observed and expected. We have to calculate the expected value of that. And this is a formula for that. We're going to see it in a minute. So observed minus expected, the square divided by expected. Yeah? And this is called as a non-parametric way, you see? Because this is a parametric because it's a variance. Variance means there is a normal distribution. And this is a non-parametric way. So one can use this test even if the data is non-parametric. Yeah? It's not a Gaussian distribution. Example. So, wow, this is a big example. So, genetic theory states that the children having one parent of blood type A and the other of blood type B will always be of one of the 3 types A, AB, and B. And that the proportion of the 3 types will, on an average, will follow this 1:2:1. A report states that out of 300 children having one A parent and B parent, 30% was found to be A, 45 AB, and the remainder was B. Now they test the hypothesis by chi-square. What is actually asking is that The meaning of this one is that 1 is to 1.5 is to 0.83. That's the meaning of this 300, right? So 30% of 300 would be 1, 45 and 300. This is a ratio, right? The question is, if this ratio is different than the theoretical ratio, according to genetic theory, right? 1 is to 2 is to 1. I mean, just by looking at this ratio, one cannot say, right? And the chi-square will help you to decide if the two distributions are, or two proportions are different or not. Yeah? So, this is the observed frequency. Yeah, we have seen that because the 30% of the 300 is the 90, then the 45% of 300 is 135, and the remainder would be 75, right? Expected. What is expected? How did I get expected? Expected is this one, because this is the hypothesis, right? That according to genetic theory. So this is my expected frequency. So what is the 300? So if I want to divide 300 children into 1 is to 2 is to 1, how would I divide? I would divide in this way: 75, 155, 75, right? So I have got observed and the expected. I take a difference, 15 minus 15, 0. Take a square according to the chi-square formula. This is the one. And then I sum it, right? I sum them up. 4.5. What is my degree of freedom? Degree of freedom is, this is 3. So 3 minus 1, that's 2. Yeah? Now you go to the table of chi-square distribution on the back of your textbook or whatever in the internet or whatever, right? Normally you don't have to do it, right? Because all the software these days will do all these things, but this is easy to understand. So you check for 2 degree of freedom with a 5% level of significance, what was the value of the chi-square? The chi-square value is 5.9. And what you got? It's a 4.5. So 4.5 is less than 5.9, so you fail to reject the null hypothesis. Yeah? So this supports the theoretical hypothesis of the genetic theory that on an average type 1 follows this proportion. If it was failed to reject, if it was accepted, right? Failed to reject meaning that it is accepted, right? But if it was rejected, then we cannot say that this proportion that we observed follows the genetic theory, right? It is not according to genetic theory. There is something has gone wrong. Good? I think this is a bit outside our day-to-day life, but I have got an example for you guys. So, but this is it's good, right? It's really nice. Just by looking at this one cannot say anything, but just by chi-square, one can say with a significance. It's different. I think this might impress you, right? So this is the outbreak of the smallpox. So you have got a vaccinated population. So there were 500 people which was got vaccinated, and the 1,500 people which was not got vaccinated, right? And across the time, they have found that the 31 people have been attacked by or infected by the smallpox. And of course, the 500 minus 31 would be that number not attacked, right? Similarly, with this 185 was attacked when was not vaccinated. Yeah, so this is how we got this table. This table is called the contingency table. 2 cross 2 contingency table, okay? Now the question is your vaccination effective? That's the question. And the chi-square will help you to answer this question. Yeah? You can, actually I have got an example for you also. But you can just imagine that in this vaccination and non-vaccination you can have a different treatment, right? Treatment A, treatment B and like that. And you have a dichotomous output. GFP positive, GFP negative, GFP positive. And you can compare the two different groups with a knockout and the wild type and like that. I have that example. But let's follow this example. So how do I do this? Step 1, recollect the formula. This is a formula, right? What is my observed? Whatever I see here, that's always an observed value. Yeah? The problem is with the expected. We have to calculate the expected value as we did last time. So the expected, I was not aware, I'm not aware of this one. So calculate the expected value. How do I do this? Just blank all these cells, you see, put all the numbers here as it is, and then it's a simple formula. What I do is 216 times 500 divided by 2000. That's the expected value. Likewise, you do it for every cell, right? Then you get this value, that's the expected values, right? And you compare, 31 is compared with 54, 216 is compared with, sorry, the 185 compared with 162. Likewise, you compare, right? Now the question is now, are they different? The observed and expected. And the chi-square will help you. So you have seen that there is a 3 groups, as we have seen, 4 groups basically. This is the 4 groups, right? The 4 groups, this is the observed frequency, 4 numbers compared with the expected 4 numbers, and through this formula, you get this 14.64, that's a chi-square value. Now what is the degree of freedom in our case? Degree of freedom is because we have this 2 rows and 2 columns, right? If you have 2 experiments and a different conditions, not dichotomous, but low, medium, and high, or any numbers, right? But it has to be interval, right? Categorical. So it is always the formula is row minus 1 times column minus 1, that is 2 minus 1 times 2 minus 1, that is 1. You go and check in your chi-square table, what is the value of, for 1 degree of freedom with a 5% level of significance, that is 3.8. Is this value more than critical value? Yes. So what we would do, we would reject null hypothesis. Yeah? Because this observed value or the chi-square value is more than the critical value for that degree of freedom. So with this one, we would say, so what was our null hypothesis? Null hypothesis was the vaccination and not vaccination, they are all the same. That was our null hypothesis. And now we got evidence that we can reject this null hypothesis, meaning that the vaccination was effective in smallpox, this example, yeah, outbreak. Okay, maybe this would impress you. So drug, I have A and B, response to the drug, yes and no, right? So I have a cross-sectional study, or what do you call this, a temporal study, let's say. And then I have this drug trial for the A and B. 153 was found to be responsive to the drug A, 50 was found to be responsive to drug B, and this is how you get a contingency table. And if you follow, you can say that the 53 divided by 193, that is a 79.27% response rate to the drug A. This is also one can, apart from chi-square, one can extract this information, okay, here, that the response rate, you can say that the response rate for the knockout was this much as compared to the response rate of wild type, whatever, according to your experiment. So this is what it is. And then, is the response rate in drug A statistically higher than the drug B? So you got this response rate, and now you have a question, right? Because is drug A better than drug B for the response? And the chi-square will help you in this one. Because we cannot apply t-test or ANOVA in this one case, because these are the proportions. We cannot, these are not means. But also, before that, one can also extract another information, another level of the information. That is the odds information. That's the odds of responding in drug A trial would be 153 divided by 193 divided by who have not responded divided by the total of them. So that's the probability of responding divided by probability of not responding. That's called as the odds of having in drug A, okay? Similarly for the drug B. So that's a 3.8, 0.72. And then we can take a ratio of this one, that's called as odds ratio. You must have heard in the literature, the odds ratio, right? So if you see the odds ratio of A versus B, that would be 5.3. So what does it mean? It means that the odds of having a response rate in drug A is 5.3 as compared to the odds of B. So one can just roughly say that drug A has to be better than drug B because it's more than 1, right? It's a ratio, so it's more than 1. But it's just, one cannot say it is significant or not. And for that, we need a chi-square test, okay? So, but because I wanted to show you, I said before, right? When you have it's a Fisher exact test. Let's see how to use a Fisher exact test for this similar example. I'm not going to go into detail of how the Fisher exact test works, just MATLAB command Fisher test, right? And then you just put this numbers, this matrix, the contingency table. and you get three values, H, P, and stats. H is equal to 1, P is very significant, right? It's less than 0.05, and the odds ratio. The stats will give you the odds ratio. That's a 5.27. Now you see this, the Fisher's has given 5.27, and what we have computed last time, we computed 5.3. So they're close together, right? Even if you do not use Fisher's, then they're close together. So this is like, one can use either way. But apart from that, Fisher's will give you the confidence interval for the odds ratio. So one can definitely say 95% confidence that the odds ratio will vary from 3.1 to 8.7. So does it include 1? No. So one can definitely say that I'm 99% confident that all the time, if you repeat this experiment, drug A would always be effective or more responsive than the drug B. Okay? And the Fisher's test will accept this hypothesis, meaning that there is a difference between these two, the drug A and drug B. That's basically the same case here. So you have the similar situation. Now it's got the wild type and the knockout, because this is with respect to mice, I thought, right? And by the way, this is not an experiment. I generated this experiment. This is a hypothetical experiment, right? So for the knockout, I thought we have the 10 mice, and out of them, when you follow them doing this experiment, you found that the 6 of them were survived, 4 were died or killed or whatever. Wild type, 2 of them were survived, 13 were died, right? And then you got this contingency table, and you want to know if the knockout and the wild type has statistical difference. Huh? One cannot use any t-test again and non-parametric Wilcoxon-Mann-Whitney, but use the Fisher test. You just plug this formula, you get this HP. H is equal to 1, P is 0.05, meaning that statistically significant, they are different. What is the odds ratio? The odds confidence interval is 1.38 to 68.78, you see? So it is always more than 1 point, it's always more than 1, right? So I can say that a wild type is more survived. I mean, the knockout has a more survival rate than the wild type in this case. Let's take this example. The same experiment, but I have changed the numbers. You see? 6, 7, instead of 2, now it's 7. That becomes 8. And if I do the same thing, H is equal to 0, meaning that I reject null hypothesis. So the p-value is not significant, and the odds ratio is 0.33 to 8.6. Does it include 1? Yes. So meaning that sometime you might get 8.6 as odds ratio, but do not believe on that. What you have to believe is that the confidence interval. If the confidence interval contains 1, meaning that it is very likely that just by chance you might get 8.6, but it is very likely that you will get 1 odds ratio, meaning that there is no difference between knockout and wild. Yeah? And then another question would be that what if I have multiple groups, right? Wild type, knockout, or what else you have? Control, I don't know, but just think of anything, right? The different, like more than 2 groups, and then more than two different variety or the categories. In such cases also one can use chi-square test. That's why it's called as a to do is that, because it doesn't make sense to have the odds ratio, because odds ratio will always based on 2 entities. So you cannot compare 3 simultaneously. So there is a Mantel-Hansel test in order to compare the 2 by 2 matrix, yeah? When you have more than 2 groups. So thank you so much. Any question? Yes?
Can you comment again on like the cutoff between the sample size, between the small sample size? Again,
Small sample size, last time, it was basically, first of all, when you say small and large, because we have to calculate sample size, right? Because sample size depends on your deviation in your readout. Yeah, so one cannot say it's a small or high. It depends on how much effect size you are targeting on. That's why it's the jugglery of calculating sample size, right? But on an average, that's a global acceptation that whatever is less than 30, that's a small sample size according to distribution. Because if anything above 30, one can use Z distribution. So more than 30, large sample size. But again, it depends on exposure, right? If your effect size is higher, right, or if effect size is lower, you need more sample size. Yeah. To see the difference between this type 1 and type 2, right? Yes. And then the next lecture we'll see this multi-parametric, meaning that if you have more than one feature for your one sample, how to look at it, because one cannot use t-test or z-test or whatever the test we have seen so far. They all fail because they all deal with only uniparametric data, right, or monoparametric features. So one features, how to deal with that, how to build a model. Okay, good. Thank you. Done? How was it?